This section examines front-wheel drive layouts. In front-wheel drive vehicles, the engine can be mounted transversely or longitudinally. Drive reaches the front wheels through a transmission and final drive unit called a transaxle. In transverse applications, the transaxle is normally mounted at the rear of the engine, and a primary shaft engages with the splines of the clutch center plate. When a gear is engaged, drive is transferred to a secondary shaft, and through a secondary shaft pinion to a helical ring gear attached to the differential case. Drive is then transferred through the differential gears to each drive shaft and into each front wheel. Universal joints are fitted at the inner and outer ends of the shafts to allow for suspension and steering movement. In this case, the engine crankshaft, transaxle shafts and drive shafts all rotate in line, which simplifies the final drive arrangement. Mounting the engine longitudinally means the drive must be turned through 90 degrees. A crown wheel and pinion is commonly used for this purpose. The transaxle can be mounted under the engine and the drive transferred by a chain from the clutch shaft to the transmission input shaft. The final drive bevel pinion is formed on the output shaft and meshes with a crown wheel attached to the differential case. The drive is transferred through 90 degrees to the drive shafts and to the road wheels. In front-wheel drive vehicles, the drive shafts transfer the drive directly from the differential to the front wheels. A short inner stub shaft is splined to the differential side gear, and an outer stub shaft is splined to the front wheel hub. Each stub shaft has a yoke or housing to accommodate a universal joint at each end of a connecting intermediate shaft. Universal joints let the shaft keep rotating while allowing for changes due to suspension movement, such as shaft length and horizontal angle, and shaft angle as the steering turns. Constant velocity universal joints are normally used to transfer power smoothly between the components. The inner universal can be a plunge or tripod type joint. The tripod is splined to the intermediate shaft and held by a circlip. A ball supported on needle roller bearings is fitted to each post of the tripod, and these slide in a trunnion inside the yoke. This caters for changes in shaft length and horizontal angle. The drive is transferred through the trunnion and balls to rotate the shaft. The outer universal joint allows greater angular changes but not changes in shaft length. It is normally a ball and cage type, with an inner race splined to the intermediate shaft. An outer race is formed in the yoke. The cage retains the balls in location in grooves in both races. The balls transfer the drive from the shaft to the hub and allow for changes in horizontal angle and for a wide steering angle to be achieved. A flexible rubber boot fitted to each joint retains grease and keeps out dirt and moisture. Where the differential is not located in the center line of the vehicle, an intermediate shaft can be fitted to maintain equal length drive shafts on each side. This keeps drive shaft angles equal on both sides and helps prevent steering irregularities and vibration. The outer end of the intermediate shaft is supported by a bearing secured to the transaxle case, and a universal joint assists with alignment. In some cases, a longer drive shaft is used on one side. A rubber dynamic damper may be fitted to absorb vibrations. This section examines front-wheel drive final drives. In front-wheel drive vehicles, the final drive gears are part of the transaxle assembly. In transverse applications, the gears are normally helical. A small pinion gear on the transmission output shaft meshes with a larger ring gear bolted to the differential case. The difference in gear size provides a final gear reduction from the transmission output to the road wheels. Normally, it is between 3.5 to 1 and 5 to 1. For every 3.5 turns of the pinion gear, the ring gear turns through 1 revolution. The ratio is not normally a whole number. This prevents the same pair of teeth from meshing every revolution and helps the gears wear evenly. Crown wheel and pinion final drives are used when the engine is mounted in line with the vehicle's centerline. Bevel gears allow the drive to be transmitted through 90 degrees. This pinion is formed on the transmission output shaft and meshes with a crown wheel bolted to the differential case. The ratio is determined by the number of teeth. Their relative position must be adjusted to keep noise and wear to a minimum. In most manual transaxle assemblies, the transmission and final drive gears are lubricated by the same oil. This section examines the front-wheel drive differential. When a vehicle turns, the outer wheel travels a greater distance than the inner wheel, so it turns through more revolutions. The differential allows the 2 drive shafts and the driving road wheels to rotate at different speeds when turning, while still applying an equal turning effort to both. Differential gears are bevel gears at right angles to each other inside a case, which is supported on bearings in the final drive housing. The ring gear is bolted to the case, so when it rotates, so does the case and the differential gears inside it. The 2 smaller bevel gears, or pinions, are mounted on a driving pin, which passes through the case. 2 side gears mesh with the pinions and are in recesses in the differential case. The drive shafts are splined to these side gears. When the vehicle travels in a straight line, the ring gear rotates the case. The driving pin and pinion gears rotate end over end, turning the side gears with them and the drive shafts. There is no relative motion between the pinion gears and the side gears. Each side gear turns at the same speed. As soon as the vehicle turns from a straight ahead position, the inner wheel slows down and its side gear turns more slowly than the differential case. The turning effort applied to the driving pin forces the pinion gears to rotate slowly on the pin. They walk around the inner side gear while still being turned end over end. This rotation of the pinion gears makes the outer side gear and its road wheel speed up by an equivalent amount. The outer side gear then turns faster than the case. This provides an equal turning effort to each drive shaft while allowing for their speed difference. In a conventional rear-wheel drive, engine and transmission are mounted longitudinally at the front. drive is transmitted to a rear axle assembly by a propeller shaft. Beam-type rear axle assemblies enclose the final drive gears, differential gears and axle shafts in one housing. Vehicles with independent suspension have the final drive unit on the chassis frame and transfer the drive to each driving road wheel through external drive shafts. Vehicles with rear or mid-mounted engines normally use a transaxle and transfer the drive to the driving road wheels by independent drive shafts. In beam axle applications, suspension action makes the final drive assembly rise and fall relative to the vehicle frame. This produces continuous change in the distance from the transmission output shaft to the final drive pinion, and in the angle between the propeller shaft and its connections. In addition, the pinion nose is forced up on acceleration and down when the brakes are applied. Despite these movements, the propeller shaft must transfer the drive smoothly. Change in length is accommodated by a sliding spline in the shaft. Angle changes are provided for by a universal joint at each end. For independent suspension, universal joints help align the transmission and final drive, and a sliding spline is still included to allow for slight variations in length. The external drive shafts to each road wheel have universal joints at their connecting points, and often a sliding spline or a plunge-type joint. Some applications use a two-piece propeller shaft. The front section of this shaft is supported at its rear end by a center bearing, bolted through a mounting bracket to the vehicle frame. Provision is normally made for adjusting the alignment of the two shafts. The most common type of universal is a Hooks joint or a cross and roller joint. It consists of a steel cross with 4 hardened bearing journals mounted on needle rollers in hardened caps, which locate the cross in the eyes of the yokes. The cross swivels in the yokes as the drive is transferred from one shaft to the other. However, the swiveling conflicts with the rotation, and in each revolution, the velocity of the yoke changes every 90 degrees. This change in the angular velocity increases as the angle between the driving and driven shafts increases. This type of joint is a non-constant velocity joint. The effect of the changing velocity can be eliminated by having identical joints at each end of the propeller shaft in phase with each other, and by having the input and output drives parallel. An increase in the velocity of the front yoke is cancelled out by a similar decrease in the velocity of the rear yoke in each revolution. In some cases, a type of constant velocity joint is fitted to the front end of the propeller shaft. This Lowbro joint has an inner race splined to the end of the propeller shaft and an outer race bolted to the connecting flange. A number of balls, retained by a spherical cage, are carried in angular grooves in each race, and these balls transfer the drive from one race to the other. The outer race is also able to move longitudinally on the inner race grooves, and this accommodates changes in shaft length. This type of joint allows the drive to be transmitted through a greater angle and minimizes vibration. Where the angle between the shafts is small, a flexible hard rubber coupling can be sandwiched between tripod flanges on the propeller shaft and the differential pinion. Since no friction-producing parts are involved, noise and vibration are reduced to a minimum. This section examines the final drive for rear-wheel drive vehicles. In a conventional rear-wheel drive, a beam axle assembly encloses the final drive gears, differential and axle shafts in one housing. A crown wheel and pinion transfers the drive through 90 degrees and provides a final gear reduction to the driving road wheels. Hypoid bevel gears are normally used for this purpose. Hypoid gears are a special design of spiral bevel gears, with the center line of the pinion below the center line of the crown wheel. This reduces the height of the propeller shaft tunnel to give a flatter floor pan. The tooth shape provides a greater area of tooth contact and therefore greater strength. In this example, the crown wheel, pinion and differential gears are mounted in a differential carrier, which can be separated from the axle housing. Taper roller bearings support the pinion in the carrier. The companion flange splines engage with the pinion splines to transfer the drive from the propeller shaft. A collapsible spacer between the bearings allows a specified preload to be set, and depth of mesh shims position the pinion in relation to the crown wheel. The crown wheel is bolted to the differential case, which is supported in the carrier by taper roller bearings retained by bearing caps and bolts. Threaded adjusting rings engage with threads in the carrier, and these are used to set the bearing preload and a backlash clearance between the crown wheel and pinion. With the carrier bolted to the axle housing, the splines on the axle shafts can engage with the splines of the differential side gears, and drive is transferred through the differential case and gears to the road wheels. In Salisbury axles, the carrier is integral with the axle housing. A removable cover at the rear gives access to the final drive components. The crown wheel is held in the carrier in a similar manner to the removable carrier type, but shims between the housing and the differential case bearings allow the preload setting and backlash to be adjusted. The pinion has a collapsible spacer for preloading and depth of mesh shims for positioning with the crown wheel. Hypoid bevel gears require special lubricants to withstand the high loads between the teeth. In light vehicle applications, the wheel end of the axle shaft is normally supported by one bearing in the axle housing. This is called a semi-floating arrangement. The axle shaft supports the vehicle mass and transmits driving torque. This section examines the rear-wheel drive differential. A rear-wheel drive differential uses bevel gears at right angles to each other inside the differential case. The two smaller pinion gears are mounted on a driving pin passing through the case. They are constantly engaged with two larger side gears located in recesses. The side gears are splined internally to receive the inner ends of the axle shafts. When the vehicle travels in a straight line, the ring gear rotates the case. The driving pin and pinion gears rotate end over end, turning the side gears with them and the drive shafts. There is no relative motion between the pinion gears and the side gears. Each side gear turns at the same speed. As soon as the vehicle turns from a straight ahead position, the inner wheel slows down and its side gear turns more slowly than the differential case. The turning effort applied to the driving pin forces the pinion gears to rotate slowly on the pin. They walk around the inner side gear while still being turned end over end. This rotation of the pinion gears makes the outer side gear and its road wheel speed up by an equivalent amount. The outer side gear then turns faster than the case. This provides an equal turning effort to each drive shaft while allowing for their speed difference. In this standard type differential, if one wheel spins, the other cannot drive the vehicle because of the differential action. Traction occurs only if both wheels can grip the road surface. Limited slip differentials allow differential action under normal driving conditions. However, when road conditions are not normal, a limited slip differential reduces or prevents differential action, so that a wheel cannot spin and drive is maintained to both wheels. This limited slip differential uses a multi-plate clutch pack between each side gear and the differential case. Each clutch pack has two different types of flat steel plates placed alternately in the pack. One type has internal splines, which mate with splines on the side gear pressure ring. The other has driving lugs, which locate in slots in the case. One plate on the outside is dished or cup-shaped to provide initial tension on the clutch pack when the two halves of the case are assembled. 4 differential pinions are mounted on 2 driving pins at right angles to each other, so that they mesh with the side gears. The pinion shafts are relieved so as not to make contact at their intersection. The ends of the shafts have 2 flat surfaces forming wedge shapes, which fit into similar wedges in the case. In straight-ahead driving, the driving force through the crown wheel to the differential case causes the pinion shafts to rotate end over end. This transfers the drive through the pinion gears and the side gears to the axles. There is no relative motion between the gears. However, the resistance at the road wheels forces the pinion shafts up the incline formed by the wedges in the case. This forces the shafts apart so that the pinion gears exert a greater force on the side gears and on the clutch packs. This locks the side gears to the case, preventing any sudden spinning of either wheel. It also assists in maintaining the straight line stability of the vehicle in crosswinds, because the locked clutches reduce yawing of the driving axles. Under normal operating conditions, the driving torque is transmitted equally to each axle shaft and wheel. However, when patches of loose gravel or mud are encountered, the ratio of torque delivered depends on the traction available at each wheel. The greatest amount of torque will be transmitted through to the wheel with the most traction. When turning a corner, the limited slip differential gives normal differential action and permits the outer wheel to turn faster than the inner wheel. At the same time, the differential applies the major driving force to the inner wheel, improving stability and cornering. This section examines vehicles with part-time four-wheel drive. Vehicles with part-time four-wheel drive are designed for optional off-road use. Four-wheel drive can be selected for abnormal surfaces and disconnected for normal road surfaces. In this application, the engine and transmission are mounted longitudinally at the front. Propeller shafts connect a transfer case which is attached to the rear of the transmission to final drive units on both front and rear axles. The beam-type axle housings enclose the crown wheel and pinion and differential gears. and the offset propeller shafts mean the drive is transmitted through short and long axle shafts to the driving wheels. Steering is catered for by mounting the front wheel hubs on large ball swivels attached to the ends of the axle housing. Universal joints are incorporated in the front axle shafts. The transfer case lets the driver select either two-wheel drive or four-wheel drive in high range or four-wheel drive in low range. A neutral position allows an accessory such as a cable winch to be driven from a power takeoff gear on the transmission output shaft. When four-wheel drive is engaged, the front and rear propeller shafts are locked together and driven at the same speed. Drive is transmitted to front and rear final drive units simultaneously. This section examines drive shafts for four-wheel drive vehicles. Propeller shafts transfer the drive from the transfer case to the final drive units at the front and rear beam axle assemblies. Each propeller shaft has a universal joint at both ends to transmit the drive through a varying angle, and a sliding joint incorporated in the shaft between them to accommodate changes in shaft length. The front axle drive shafts are enclosed within the axle housing. They are splined at their inner end to the differential side gears and to the front hubs at their outer end. A constant velocity joint in each shaft allows for steering movement while continuing to transmit the drive. The rear axle drive shafts are splined at their inner end to the differential side gears. A flange on the outside locates on studs on the rear hub to transfer the drive to the wheel. The rear hub, which is a fully floating type, is mounted directly onto the outside of the axle housing and is independent of the axle shaft. Two tapered roller bearings support the hub on the housing, and adjustment is provided to maintain end float within specifications. The mass of the vehicle and all forces from forward motion and side thrusts are transferred from the wheel directly to the axle housing through the tapered roller bearings. The axle shaft is relieved of all these forces and is used only to transmit torque. In full-time four-wheel drive vehicles, drive is transmitted through the rear final drive to the rear wheels and through the front final drive to the front wheels at all times. The final drive gears are normally a hypoid bevel crown wheel and pinion type. The same gear ratio is used for both front and rear units. This section examines the transfer case. This transfer case is bolted to the rear of the transmission. Drive is transmitted from a helical gear splined to the output shaft, through an idler, to the output shaft pinions. They are free to rotate on needle roller bearings on the rear section of the output shaft. They have external dog teeth facing an engagement hub and sleeve splined to the shaft. When two-wheel drive high range is selected, the engagement sleeve engages the dog teeth of the smaller output pinion. This locks the pinion to the shaft and provides a high output speed range. Drive is transmitted through the larger pinion of the idler gear and the locked output pinion. This rotates the rear section of the output shaft, which is coupled to the rear final drive unit. The idler gear pinion transfers the drive from one shaft to the other and has no effect on the ratio. For four-wheel drive high range, splines on the rear section of the output shaft are also engaged by a separate engagement sleeve, splined to the front section. This locks front and rear sections together, providing a high output speed to all four wheels. For four-wheel drive low range, the transfer case engagement sleeve engages the larger output pinion. At the same time, the four-wheel drive engagement sleeve locks into position. Drive is transmitted from the transmission output to the large idler pinion, through the smaller idler pinion to the larger locked output pinion. This double reduction in the gear ratio provides a low output speed range to both front and rear wheels. With the engagement sleeve in a central or neutral position, the main transmission can drive an accessory like a cable winch. The idler gear and output pinions rotate, but no drive is transmitted to the output shaft. On part-time four-wheel drives, the front wheels and axle drive shafts are splined together through the differential side gears. When the vehicle is using a two-wheel drive range, the front axle drive shafts, final drive assembly and front propeller shaft all turn with the road wheels, but do not transmit any drive. Freewheeling hubs can be installed on the front hubs to disconnect the hubs from the axle shafts and prevent rotation of the front axle components. This reduces wear and noise and improves performance and fuel economy in a two-wheel drive range. When lock is selected on this manually engaged type, it acts on this sleeve. It has external splines into the freewheel hub body and internal splines to engage a hub on the axle shaft. The sleeve locks the two components together. In a four-wheel drive range, the drive is transmitted from the axle shaft through the clutch to the hub and road wheel. When free mode is selected, the compressed spring pushes the clutch sleeve out of engagement, leaving the wheel free to rotate without turning the axle shaft. This section examines differentials for part-time four-wheel drive vehicles. In part-time four-wheel drive vehicles, differentials are fitted to both front and rear axle assemblies. When a two-wheel drive range is selected, the drive is transferred through the rear final drive and the differential gears to the rear axle shafts and road wheels. The differential gears allow the rear wheels to rotate at different speeds when the vehicle is turning, while continuing to transmit an equal turning effort to each wheel. When four-wheel drive is engaged, the drive is transmitted through both front and rear axle assemblies, and differential action occurs in both. However, in a turn, side swiveling of the front wheels for steering makes the front wheels travel a greater distance than the rear wheels. This causes a difference in the rotational speeds of the front and rear wheels. Since there is also a difference between inner and outer wheels, each axle shaft now turns at a different speed. Differences in speed can also arise from differences in tread wear between front and rear, or in tyre inflation pressures. Since front and rear propeller shafts are locked together at the transfer case, the difference in speed cannot be absorbed in the transmission, and the transmission drive line can be subjected to torsional stress. In off-road conditions, differences in speed can be absorbed through slippage of the tyres on the ground surface. On firm road surfaces, only two-wheel drive should be engaged. This is to prevent excessive tyre wear and possible damage to the transmission driveline. This section examines the layout of full-time four-wheel drive vehicles. In this four-wheel drive vehicle, the engine and transmission are mounted longitudinally at the front. Propeller shafts transfer the drive from a transfer case on the rear of the transmission to final drive units at front and rear. The beam-type axle housings enclose the crown wheel and pinion and differential gears, and the offset propeller shafts mean the drive is transmitted through short and long axle shafts to the driving wheels. A third differential is in the transfer case between the front and rear output shafts to the final drive units. This allows for any difference in speed between the front and rear output shafts when the vehicle drives in high range. In addition, a viscous coupling limits the third differential action if any of the drive wheels spin. Torque is automatically transferred to wheels that are not spinning. In extremely slippery conditions, engaging low range automatically activates a differential lock to prevent third differential operation. This section examines drive shafts for four-wheel drive vehicles. Propeller shafts transfer the drive from the transfer case to the final drive units at the front and rear beam axle assemblies. Each propeller shaft has a universal joint at both ends to transmit the drive through a varying angle, and a sliding joint incorporated in the shaft between them to accommodate changes in shaft length. The front axle drive shafts are enclosed within the axle housing. They are splined at their inner end to the differential side gears and to the front hubs at their outer end. A constant velocity joint in each shaft allows for steering movement while continuing to transmit the drive. The rear axle drive shafts are splined at their inner end to the differential side gears. A flange on the outside locates on studs on the rear hub to transfer the drive to the wheel. The rear hub, which is a fully floating type, is mounted directly onto the outside of the axle housing and is independent of the axle shaft. Two tapered roller bearings support the hub on the housing, and adjustment is provided to maintain end float within specifications. The mass of the vehicle and all forces from forward motion and side thrusts are transferred from the wheel directly to the axle housing through the tapered roller bearings. The axle shaft is relieved of all these forces and is used only to transmit torque. In part-time four-wheel drive vehicles, drive is transmitted through the rear final drive in all drive ranges. Drive is only transmitted through the front axle final drive when a four-wheel drive range is selected. The final drive gears are normally a hypoid bevel crown wheel and pinion. The final gear ratio reduction must be the same in both front and rear axles, so that when four-wheel drive is engaged, the driving wheels rotate at the same speed. The crown wheel is bolted to a differential case, and drive is transmitted through the case and differential gears and axle shafts to the road wheels. taper roller bearings support the differential case and the pinion in the carrier. Provision is made for preload and backlash adjustment, and for positioning the pinion in relation to the crown wheel. This section examines the transfer case. In this application, the transfer case is bolted to the rear of the transmission. Drive is transferred from the transmission output shaft to an internally splined helical gear on the transfer case input shaft. This gear is constantly meshed with the larger of two idler gear pinions. They are constantly meshed with the high and low output pinions on the transfer output. The low-range output pinion is bolted to a differential case, which contains the third differential gears. The high-range pinion can rotate on needle roller bearings on one side of the case. The idler gear pinions are also separated, with the smaller low-speed gear free to rotate on needle rollers on the idler shaft, formed with the high-speed gear. A common selector fork links a splined engagement sleeve on the idler and a similar sleeve on the output. Moving the fork to engage high range locks the high output pinion to the differential case. Drive is transmitted at a 1-to-1 ratio through the larger pinion of the idler gear and the locked output pinion to the differential case. It is then transmitted through the differential gears to the front and rear output shafts. Engaging low range moves the selector fork in the opposite direction. This locks the low idler gear pinion to the idler shaft. From the transmission output, drive is transmitted to the large idler pinion and through the smaller locked pinion to the low range output pinion, bolted to the differential case. This double reduction provides a low output speed ratio of 2.48 to 1 to both front and rear shafts. In addition, when low range is selected, a geared electric motor automatically operates an engagement sleeve splined to the front output shaft. It engages mating splines on the differential case. This locks out all differential action between the front and rear output shafts, so it should only be used in off-road situations. In high range, the differential lock is disengaged. Differential action is catered for by the differential gears located in the output case and splined to the output shafts. This allows for a difference in speed between front and rear wheels when the vehicle is on firm road surfaces. This section examines transfer case differential action. In this application, when high range is engaged for driving on firm road surfaces, differences in speed between the front and rear wheels are catered for by the third differential gears in the transfer case output. However, the third differential operation means that if a front wheel spins on a slippery surface, no drive is transmitted to the rear. To reduce this action of the third differential operation, a viscous coupling unit between the differential case and the rear output shaft acts as a limited slip differential. The outer plates of the viscous coupling are splined to the differential case, and the inner plates are splined to the output shaft. Torque transfer through the coupling is achieved by the high viscosity of the silicon fluid sealed in the unit. As the fluid expands when it is heated, the unit is only filled to about 80% of its capacity. The outer plates are separated by spacer rings. The inner plates are free to move axially and are not mechanically centered between the outer plates. In normal driving conditions, the third differential operates to provide the small degree of differential action necessary. There is only a minor speed difference between the viscous coupling plates. However, when a wheel spins, there is a higher level of third differential action and a greater speed difference between the front and rear propeller shafts. This speed difference also applies to the viscous coupling plates. Fluid in the unit is sheared by the relative motion between them. This shearing action causes localized expansion, forcing the inner plates into contact with the outer plates. The degree of locking achieved depends on the severity of the wheel slippage occurring. 100% locking is only achieved under severe conditions. When the plates are fully locked, the fluid starts to cool, and the cycle of shearing and locking recommences.